Okay, normal distribution. So that's what we're talking about today. This is a big thing in stats. Okay, so we're explore quantitative data. So always plot your data, make a graph. We've already done this, right? Look for overall pattern. We've done that with shape, center, variability, outliers. Calculate numeric summaries. We've done that with one variable stats, right? So when there is a regular overall pattern, use a simplified model to describe it. So a regular or normal pattern, kind of bell-shaped. It is surprising how often this comes up in real life. Okay, so let's see what this model is about. So a normal distribution is a distribution with a very unique shape. It's called a normal curve. Kind of looks like that, like bell-shaped. So we describe it as symmetric. You want to know all these things about a normal distribution. Single-peaked, mound-shaped, sometimes we use those terms, called a normal curve. Any normal distribution is completely specified by two parameters, its mean and the standard deviation. If you remember from last chapter, we were talking about if the data is approximately symmetric, then use mean and standard deviation. That's what we use with the normal curve. The data is always approximately symmetric. By the way, you can tell this data is not perfectly normal. So usually we use terms like approximately normal whenever we use the word normal. In fact, don't even just call something a normal curve. Call it approximately normal. Just protect yourself. It's the way we almost never call something a normal curve. It's always approximately normal. It's never perfect data. So in this one, two normal distributions showing the mean and the standard deviation. So those are both normal distributions. So it can be kind of tall and skinny-ish and sometimes wide. And so those can both be considered normal. Depends on how you draw it, what the size of the standard deviation is, but it's measuring this in terms of standard deviation like we did with Z-scores. Kind of relates to this. Okay, two normal distributions. So what is the shape? Again, symmetric, single-peaked, unimodal, and mound-shaped, also called bell-shaped. Center is located at the balance point, or right in the middle there, and it's the same as the median. We think the mean and median should be about the same for something that's approximately normal. And finally, the spread is in terms of standard deviations. We're measuring it, the width, in terms of standard deviation. We'll talk more about that in just a minute. I like starting with this. When I sketch a normal curve, that's exactly how I sketch it. I put 7 tick marks, so 1 in the middle and then 3 to the right and 3 to the left of that 1 in the middle on the bottom. That's exactly what I do. So consider a car going 62 miles per hour with a mean stopping distance of 155. So mean of 155, I would put in the middle. Standard deviation is 3. So in fact, I know there's an easy one to do in our head, but this is what I do with my calculator. So I might type in 155, press enter, put plus 3, and I just type plus 3. It says answer plus 3. If I press enter 2 more times, it gives me the next 3 numbers. So to the right of that, I'm going to put 158, 161, 164, type in the mean, subtract 3, and do that 3 times, and you'll put those numbers to the left. So 146, 149 from left to right there, and you'll have all those numbers in the right spot. That's especially helpful when it's decimals. It was easy to do that one in your head. I'll show you again that technique, but it's really helpful. Start by labeling the mean, put that in the center, right? That's the mean and the median, or approximately the median. Standard deviation is 3, so we're going to go to the right 3, to the left 3. That's 1 standard deviation to each side. That's called within 1 standard deviation from the mean there is from 152 to 158. Within 2 standard deviations of the mean would be from 149 to 161, and within 3 would be from 146 to 164. You can tell already, probably, the vast majority of the data is going to be within 3 standard deviations. There might be a little piece out on each side, but very small. Most of the data is going to be within 3 standard deviations. In fact, you need to memorize these within 1 standard deviation. Just to remind you, that's 1 standard deviation. So when we say 1 standard deviation, it means below and above. So I went up 3 and down 3. So one standard deviation is between 152 and 158. That's the interval that stands for one standard deviation. So how much of the data is within one standard deviation? About 68%. How much of the data is within two standard deviations? 95%. And how much was in 3? The vast majority of the data, 99.7. You do need to memorize those numbers. We will use those for sure in this class. It's called the empirical rule is the name of that. That's for perfectly normal. So we use this for approximating things. If we don't want to calculate things exactly, we can use it for approximation. So about 95% of scores are within two standard deviations. I don't know if you remember, but we said that anything 5% or less is considered unusual. So if 95% are within two standard deviations, anything within two standard deviations is not that unusual. But if you go more or less than that, more than two standard deviations in either direction, that is less than 5%. So it gets to be unusual there. And does it make sense that on the left side, there'll be 2.5% to the left? On the right side, there'll be 2.5% to the left, approximately. Look again at the model. What percent of cars would, so if you drew it out, you go, okay, 68% of the cars are within one standard deviation. That's between 15 and 152 and 158 there. And then the other, sometimes I even do this. So this might help you. So I'm just going to draw out my thinking on this. So it might help. So let me get to this guy. So if I draw, let me see. Okay, so I'm going to draw a normal curve. It's not that beautiful, but that's okay. So we think that, that's one standard deviation. So that's 68% of the data goes between there. So I prefer to think of this as 34% is on each side. To make sense, you split that in half. So 34% is within each side there. Then we think within two standard deviations, we think the number is 95%. So that's 95%, which means, let's get our calculator out so we can think this through. So to calculate this, if we do 95 minus 68, so 95% minus 68. So the part on each side will add up to 27%. Well, there's two parts on each side there. So we have like, let me see. We have this part. Whoops. No, I don't want to do that. I thought I could choose the color. Maybe I can't choose the color here. Okay, I'm just going to go back to a pen. Okay, hopefully this works. Okay, so we do 27, but if we do 27 divided by 2, 27 divided by 2, it's 13.5. So there's 13.5 over here percent and 13.5% over here. I think this is helpful for you. It should be. And then 3 standard deviations within 3 is 99.7, 99.7. So let's subtract that. So on our calculator, let's do 99.7 minus 95. So minus the 2 standard deviation amount. So 4.7 is in this kind of third part there. So I think I have, it's doing disappearing ink on me. It's kind of funny though. Okay, so let's go to the pen. Okay, so this was 13.5. It's funny, that was disappearing ink, 13.5%. And so if I take that 4.7, I divide that by 2, I have 2.35 in the next part here. So 2.35. And I also have 2.35 within, that's within 3 standard deviations from the second to the third there. There's actually a little piece out here. So I think it's 0.15 is on the very, very end on both ends. So 0.15, I kind of ran out of room there. But 0.15 on each end there. So when it was doing, so I think the problem, it was saying this area, and all this. So to me, I thought about it this way, 50% is to the right. So I know that's 50%, plus the 34% is 84%. So that's how I did this problem. I broke it up into half. So to the right of the 50% point is 50%. And then 34% is within one standard deviation below there. So I just did 50 plus 34 to get the answer of 84 there. 84%. So about 16% would take, no, that's about 84% would take more than 158. What's the question asked? Does the stopping distance follow normal distribution? What percent of cars would take more than 158? So I would think of it as 50. So on this problem, actually, I did it differently. So I would have said 50%, which is everything to the right of the median and mean there, minus that area to the right, that 34% right here. So minus 34% is equal to 16%. So that's how I did it. You can do it different ways. They did it a couple different ways there, but that's the idea of it. 16% of the cars would be more than 158. Is it risky to assume a distribution is approximately normal? It can be. If the graph is clearly skewed, multiple peaks, isn't bell-shaped, that's enough evidence to go, this is not normal, right? Even if it looks roughly symmetric and bell-shaped, you can't always assume. So we don't always do this, but sometimes we'll do this to check, especially when they ask us to check, is this indeed a normal curve or not? And so, or approximately normal. So we can use the empirical rule to test. Look at this data. By the way, we would never in real life actually test this data because it's clearly skewed right. It's not normal, and we would not call this normal. But let's do the test to see if it is normal or not. So the test would be this. Remember, 68% of the data is within one standard deviation. So using the mean and standard deviation listed, so the mean is 1.825, standard deviation is 1.394. So you would go, in your calculator, you could go, okay, 1.825 plus the standard deviation is 1.394, and then well, let me just copy and paste. And this time I'm going to subtract. So how many dots are between 0.431 and 3.219? Okay, so I see 4 are off too far to the left of that. 1, 2, 3, 4 are too far to the right of that. So there are 8 dots that are not in that labels, in that interval. So if there are a total of, hopefully it tells us here how many dots there are, n is 40, right? So 8 dots are not there. So 32 divided by 40 is going to be giving the decimal. So 80% are within one standard deviation, because that's one standard deviation from the mean. Well, that's not good. We wanted 68%. We could probably stop right now and say this is not normal. But what they did is they tested it. They said about 63 are within one standard deviation of the mean. Oh, this is a different problem. Sorry. I thought they were going to do that one. They didn't do it because it was massively skewed, I guess, right? So they took this one. So let's do this one. We can think this through. So we would start with the mean, 106.883, plus the standard deviation of 19.484, and then that one minus. So that'll give us one standard deviation each direction. So how many dots are between 87 point something and 126 point something? So I see there are 1, 2, 3, 4, 5, 6 to the right of 126, and then 87. there are 1, 2, 3, 4, 5, 6 to the left. So I've got 12 dots that are not in that interval. So 77 minus 12 is 65. So 65 divided by 77 is 84%. I was hoping for 64% or 68%. Got way too much, right? So we got 63, they counted 63 out of 77. 68% should, so 82, 84, any of those you get, it's definitely not the 68% we wanted. So this is not approximately normal. We don't really have to keep testing there, really. The amount of ice cream in a random sample of 45 double stuffed Oreos is listed below, okay? So here we are. So we've got that. Hopefully, is this distribution approximately normal? Well, if they gave us, I didn't have to type that all in my calculator. I was hoping they would give us the summary stats. They did, right? So using the summary stats, let's figure out what one standard deviation is, right? So if we start with a mean of 6.742 plus a standard deviation of 0.184, and then minus the standard deviation of 184, that should be one standard deviation above and below. So how many of those numbers are bigger than 6.558? So I see what that line is at 6.926. So then you're going to count how many terms are bigger or smaller than 6.558 and bigger than 6.926. So I think they did that. 32 of the values are within the one standard deviation. So that's 71% of the data. That's not too bad. We're looking for 68%. We got 71. I can live with that. It's kind of a judgment call, but I'm not throwing it out yet. 43 of the 45 values are within two standard deviations. So to get two standard deviations, so you could take this and do 2 times that, and then 2 times that. So you're subtracting two standard deviations or adding two standard deviations to the mean. So bigger than 7.11, I see one value. Smaller than 6.374, I see one value, I believe. So there's only 2 out of, so 43 of 45 are within two standard deviations. So that's 95.6. I'm very happy with that number. It's pretty close to 95%. And then all the values, if you add one more standard deviation, all the values are within that. So that's pretty close to 99.7. So is this, sure, we're going to call this approximately normal. That's close enough. So there's not a defined limit, but you kind of look at it and go, is it close enough? Yeah, that's pretty good. It's approximately normal. You can tell it's kind of has a weird little skew there a little bit, but it's mostly approximately symmetric and it works. Dairy farmers are a big business. The size of making herds has grown larger over time, so farms are producing more milk than ever. Research on that reveals the amount of milk a cow produces during each milking is approximately normal with a mean of 12.39, the standard deviation of 4.32. Draw the normal curve that approximates the distribution of milk production. Label the mean and the points that are 1, 2, and 3 standard deviations from the mean. So you start with, draw the normal curve, put the 7 tick marks below, the 1 in the middle and 3 to the right of it and 3 to the left of it. And then you start figuring out the mean and standard deviation. So this is where your calculator really comes in handy, I think, to figure out those values. So I always start with the mean. It's 12.39. I press enter. Then I hit plus 4.32. And I hit enter 2 more times. It's going to keep adding that. So those are the numbers to the right of the mean that I'm going to put. Then I type in 12.39, press enter, and hit minus 4.32, and I press enter 2 more times. And those give me the 3 numbers to the left of that. So you get these numbers, which is what we just got, I believe, doing that in the calculator. So it just helps you get there faster if you do that way in the calculator. I highly recommend it. And don't forget to put the title on here. So this is milk production in kilograms. So always put the unit. If it has a unit to it, try to put the unit in the title there. And that's the drawing of this. That's what we expect you to be able to do, is draw the normal curve. Oh, Dr. J, the NBA. So he was great. He had this really amazing dunk that's still popular today. He was described as the first player to play the game more above the rim in the air than below it. He just dunked a lot. He did a lot of cool stuff in the air. Over the course of 977 game career, the distribution of Dr. J was approximately normal with a mean of 22 and a standard deviation of 7. So you would then draw this normal curve, right? So you draw it, scale it out, and you get, from 1 to 43 there. About what percentage of games did he score between 15 and 36? So the way this works is if you draw this out, so the mean is 22. 7 is pretty easy to do in my head. So this is 29, 1 standard deviation to the right, 36, I believe, and running out of room, but 43. And then 1 standard deviation to the left, subtract 7, so 15, subtract 7 is 8, subtract 7 is 1. So we get these numbers. So from 15 to 36. Oh, that's so nice that they picked numbers that were on our, exactly standard deviation. So remember, 34% is here, 34% is here. I think that was 13.5 right here. So if you kind of do it that way, you go, okay, add those numbers up and you get it. So that's the way I do it, is I just have those numbers memorized. They did 95 minus 68, which is 2 standard deviations minus 1 standard deviation of the empirical rule, and divide it by 2 to get that piece, which is what we did when we first created that. So the answer there was about 81. If you add those numbers up, about 81.5% of his games, he scored between 15 and 36 points. So most of his games he scored between there. Finally, the last question. During the NCAA Women's Gymnastics Championship, 24 gymnasts competed in the balance beam, led by a person from Oklahoma University, won back-to-back championships, won 6 of 9. I didn't know that. So the dot plot and summary stats for the individual team balance event are there. O'Keefe earned a 10, a perfect score. I see her. I don't know if she's an outlier, but she's close. There's some outliers on the left for sure there. Is the distribution of the balance beam scores approximately normal? We can just stop right now and go, no, it's skewed left quite majorly. It is not normal, but give appropriate evidence. So if we wanted to test it, we could test 1 standard deviation. So you get your calculator out and go, okay, let's figure out what 1 standard deviation is. So you go, the mean is 9.842, plus standard deviation of 0.202, and then that minus 0.202. So the first standard deviation is between, one standard deviation in either direction is between 0.9 or 9.64 and 10.044. 9.64, there's nothing there, and 10.044. So all these points on the right, not the 2 outliers on the left, are within 1 standard deviation of the mean. So if there were, how many players? There 24. So 22 of the 24. So you would do 22 divided by 24, which is way more than 68%. 91.7%. You could just stop there at that point and say, we were expecting 68%-ish, and we got 91.7%. This is not normal data. There's not even approximately normal. That's your lesson for today.